screen. So these are the, okay. So can everyone see those notes up there? Good.
Yeah, we can see them.
Yeah, right. So I'll just ask you for a bit of feedback as we go, because we've had some internet issues at various times. So just I'll just ask you and just say yes or no, whatever. We'll try and sort it out if we have any problems. So we're going to talk about application and selection of air system equipment, other equipment to what we've already discussed. We've talked about chillers and pumps and water systems, air systems, DX, and so on. But this is getting in a bit more detail about some of the other components of air systems. And the topics today: air filters, weatherproof louvers, and flexible ductwork. These are all day-to-day things that we deal with, and probably you may take with a grain of salt, but in actual fact, it's important to be careful with the details with these things. So air filters, every air conditioning system, I'll highlight that so you can see where I'm reading. Every air conditioning system and some ventilation systems will have air filters. The purpose of the filters is to remove dust and particulates from the air before it passes through the cooling and heating coils and supply air ductwork. That's one purpose. Other specialised filters are used for applications such as grease removal, odour removal, and in medical pharmaceutical type requirements, clean rooms and so on. With the non-ducted fan coil units, such as a wall-mounted fan coil unit or a cassette unit, filters are supplied with those units. We don't need to worry about that. If you're using those systems, the filters come with it. In ducted systems, the filters have to be selected to suit the type of system and filtration requirements. And the filters are normally panel type or deep bed type. In laboratories, healthcare, pharmaceutical, clean rooms, and similar critical projects, we often use HEPA filters, high efficiency particulate arrestants. These filters have an efficiency greater than 99.99%. Keep going with the nines because it's 99999, but also have a very high pressure drop. So you need to be aware that the HEPA filters do create a high pressure drop when doing your fan static calculations. And if you do have HEPA filters in a project, they're not always available off the shelf. Some standard ones you can buy straight away, but if you're doing an operating theatre in a hospital or something like that, it could be 3 or 4 months delivery on those. So when you're looking at your program for engineering and procurement, be aware that some things are not available straight away. In some applications, carbon activated filters are used for removal of odours or chemicals in gaseous form. We'll talk a bit more about all of these in a minute. For kitchen exhaust systems, grease filters are required in the exhaust hood. The filters can be fixed panel type or washable type or proprietary type within specially designed exhaust hoods. So you can buy standard filters, which can be, or the way they normally do it is just take them away and replace them, clean them, bring them back and replace them again. So you have this ongoing service cycle of cleaning and replacement. Filter ratings. So filter performance ratings are based on the filter arrestance or efficiency. Excuse me, I've got a bit of a cough today. To test dust number 4 or number 1 respectively in accordance with AS 1324 Part 1. So there's a standard that you can go and have a look at if you want to find out all the details about how the filters are tested. In Australia, the most commonly used filters for air conditioning are rated at G4, F5 to F9 in order of increasing efficiency and accordingly increasing pressure drop. HEPA filters are typically rated at H14. International ratings are classified differently to Australia, but basically cover the same range of efficiency. The Aerotechnical Handbook contains a useful table to compare Australian, European and US classifications. Now, I've mentioned this because this is helpful information to you. As you deal with filters, you're going to want to know the differences between the filter ratings. So I've got, I'm just going to put up this is out of the Aerotechnical Handbook, which I mentioned over and over again. Morning, Jock.
Morning.
This is the Aerotechnical Handbook. You guys in New Zealand, this would be available to you. It's available online. You can buy it if you don't already have it. But it's got almost everything you're going to need to know. If you're ever looking for a good reference, this is a good one to get. I wanted to show you this because sometimes you'll see, if you're looking at filters, they might give a MERV rating, MERV rating, which is the American rating. So this is US ratings here, ASHRAE 52.2 MERV ratings, okay? On the left-hand side here is the Australian ratings from AS 1324, G1 through to F9. Generally, we don't use anything less than G4. If you're dealing with panel filters or deep bed filters, well, panel filters, G4 or F5, and then deep beds, F6 to F9. So this is something that you're going to see again and again when you're dealing with filters. And this table is very useful. So G4, normally used for fan coil units for small applications, has an efficiency, well, it's not rated under Australian, but under the ASHRAE ratings, it's 20% to 40% on test dust number 1, our equivalent test dust number 1. And then from F5 onwards, it goes up. F5 is 40 to 60, F6, 60 to 80, and so on. It doesn't seem like much information you need to know at the moment, but beware of it because it will come up. Now, there's a table here as well, which gives minimum filter ratings required under AS 1668 Part 2. So greater than or equal to 1,000 litres a second ducted has to be G4, at least. G4 or F5, or higher, depends on the application. Greater than 1,000 litres a second non-ducted is also G4. So that's probably better than the standard filter that comes with the non-ducted unit, but you probably don't get many applications of that. Less than 1,000 litres a second ducted, G2, etc. So, and I've got there's another table out of the Aerotechnical Handbook, which gives a bit of a guide on the applications. So let's ignore G1 to G3, but for G4, high-level pre-filtration, minimum commercial building filtration. So generally with fan coil units, you have G4 filters. Anything above that, you're going to F5 through to F9, and they would normally be deep bed filters. Okay. Move on. NCC Part J 5.4 specifies the maximum allowable pressure drops for clean filters when installed in the index run. So that's the worst case of the ductwork, either in accordance with table J4E or at a face velocity of 2.5 metres a second. In table J54E, the minimum efficiency reporting value of 9, 11, 13 and 14 is equivalent to F5 to F8 in Australia. So what I've just said previously helps you read these sorts of tables. So here's the NCC section, J5.4. And Part 2, J54D Part 2 talks about HEPA filters, resistances, pressure drop of 200 pascals when clean, or, that's important, that or the filter design pressure drop when clean at an air velocity of 1.5 metres per second. This is all stuff that you just need to be aware of, because when you're doing your static calculations and selecting filters, you have to comply with the NCC. Well, in Australia, you do anyway, but I'm not sure whether New Zealand uses similar things, but this is what we use here. Any other air filter, now this is any filter now, apart from a HEPA filter, the pressure drop specified in table J54E, which is this table here, and it refers to the MERV values. So 9 to 14, that's the American rating or ASHRAE rating, and the maximum pressure drop when clean, or the filter design pressure drop when clean at an air velocity of 2.5 meters a second. So that's all the stuff you need to comply with, and it's a matter of knowing where to find all this information. So again, filter minimum efficiency reporting value. That's the ASHRAE reference, and going back to the ERA. So MERV, it's talking MERV 9 to 14, which is roughly equivalent from F5 to F8. So when selecting filters, take care to ensure compliance with the required filter rating and the NCC maximum pressure drop requirements. The NCC does give you a bit of flexibility there, because it's referring to 2.5 meters per second face velocity, which is probably the highest you'd ever want to go. Okay, we'll talk about panel filters, commonly used in ducted fan coil units, and also used as pre-filters in air handling units to prolong the life of deep bed filters. So you have two filters in series, panel filter and the deep bed. Sizes vary to suit the many different fan coil unit sizes, and some manufacturers will custom make panel filters to any size you want within reason. The filter rating is normally G4 or F5, achieving more than 20% efficiency on number one test dust. So that's important. In Australia, that's very important. And if you're looking at AS 1668 Part 2, it gives you some concessions on outside air quantities, provided you achieve more than or greater than or equal to 20% efficiency on number one test dust. So we're talking about G4 and better. Nominal thicknesses of panel filters are normally 25 millimeters, 50 millimeters, and 100 millimeters. 25 thick filters should be selected at face velocities up to about 1.8 meters a second. Now, this is just sort of rule of thumb, but keeps the pressure loss down, and because the 25 millimeter filter or less doesn't have a great surface area, reduce the velocity to allow it to work more effectively. 50 millimeter and 100 millimeter filters can be selected at face velocities up to 2.5 meters a second. And as the filter thickness increases, the filter surface area also increases. I'll show you a picture of one in a second, providing a higher airflow capacity for minimal change in pressure drop. Bear with me for a sec. So this is a typical panel filter. You can see the folds in the filter, and so that's probably a 25 millimeter filter sitting on top, maybe 100 underneath.
Give us.
So those folds.
Just loading, Peter.
Sorry. Oh, it's loading.
Just haven't loaded on our end. Okay, yeah, that's it now. Thanks.
Okay, sorry. Yeah, so sitting on top there is probably a 25 millimeter panel filter, underneath 100 millimeter. And because of those folds, you can appreciate that the deeper the filter gets, the more surface area you get. So you actually increase the capacity, the airflow capacity of the filter without affecting the pressure drop. So this table here gives details for 25, 50, and 100 millimeter, the ratings G4 through to F5. And in the right-hand column is the pressure drop at 2.5 meters a second face velocity. 2.5 meters a second is what they're tested at. That's why they give that rating there. But you might choose to use a lower face velocity to get the pressure drop down and improve the effectiveness of the filter. The data I'm going to show you as we go through is from AES Environmental, and their website's there. It's actually in the notes as well. It's an Australian company. The filters are made in Australia. Years ago, probably 15, 20 years ago, email air handling were the dominant filter suppliers in Australia. So that AES Environmental manufacture email air handling filters. So it's the information is quite comprehensive and useful. When you're selecting filters, you're going to find there's a number of suppliers out there, and the information that you get may be a bit confusing because they'll present it in different ways. I just find this information easy to follow, and the filters are made in Australia. So now we're going to talk about deep bed filters. Commonly used in ducted air handling units, but not fan coil units due to the access requirements. Deep bed filters are normally pulled out horizontally from the back. So you've got to be able to get into the plenum to be able to get them out. So with an air handling unit, you have that plenum accessible so you can walk inside, or from the back, get the filters out. You can't do that with a fan coil unit, generally speaking. You can get them on slides, but they're very difficult to deal with for maintenance. I'm having some technical issues here this morning. Sorry, guys. Okay, I'm back again. So the filter rating, nominal face sizes for deep bed filters are normally 600 by 600 or 600 by 300. So one we call a full filter, the other is a half filter. Filter rating is normally F6 to F9, achieving from 60% to more than 95% efficiency on #1 test dust. So I will show you some deep bed filters, again from the same source, AES Environmental. So that's what they look like. Normally 600 by 600 nominal size for the face, and the depth of the filters, or the length, there is around 600 millimeters. It can be a bit more or a bit less. We used to be able to get 300 deep filters if you've got a very tight space in an air handling unit, but generally around 600 millimeters. So again, there's all these ratings, F6, F7, F8, F9, and the technical details, the sizes, airflow capacity and resistances. And again, these resistances are at 2.5 meters a second, which is the design velocity when you're selecting filters, no higher than 2.5. It's actually based on, like these numbers have been around for years, before metric even came in feet and inches. 600 by 600 was 2 foot by 2 foot. So they've changed the numbers of them, but it's based on the same information. 944 litres a second is for a 600 by 600 filter is 2000 CFM. It doesn't hurt to be aware of some of these, where they've come from. So 2 foot by 2 foot, 2000 CFM, that's what it's based on. So it's been around for years, nothing's changed. So nominal thickness or depth of the filters is around 600, as I said. Shorter filters can be procured if sufficient space is not available. The filters are normally selected at face velocity up to 2.5 meters a second, but remember that compliance with the NCC pressure drop requirements is necessary. HEPA filters are designed for use in critical environments where human life could be at risk or extreme cleanliness is required for a process and therefore have very high efficiency ratings. So H14, which is greater than 99.99%. Nominal sizes vary depending on the application, but common sizes are 600 by 600 or 600 by 300 with variable thicknesses. They also have very high pressure drops. And the design face velocities vary depending on the application, and this will affect the initial pressure drop. So that's important when you're looking at HEPA filters. Different applications will have different design face velocities. So for an operating theatre, for instance, it might be as low as 0.6 meters per second. If you've got HEPA filters arranged over an operating table, you don't want air blasting down on the patient. So it's normally about 0.6 meters per second for that application, but other applications will be different. So you need to look at all this technical data which is available, talk to the suppliers, look at all the regulations and determine what you need. I can't cover it in this short session. NCC again, Part J4D specifies requirements for maximum pressure drop for HEPA filters. Normally in fan static calculations, you'd allow up to 400 pascals for a loaded HEPA filter with an initial allowance of about 200. So that's a large increase in pressure, and that's going to dominate your fan static calculation if you've got HEPA filters. Okay, so the increase in pressure as the filter loads will cause, obviously the statics going up, your airflow will reduce. So it's common to provide fan speed controls to ensure that the airflow remains constant as the pressure drop increases. So we are using HEPA filter. Again, I'll refer to an operating theatre. Operating theatres require constant airflow, certain number of air changes per hour. They also are required to maintain a pressure differential between a positive pressure differential between the operating theatre and the surrounding areas, which might be 30 pascals. So if your airflow is dropping off, then you're losing your pressure differential, you're losing the circulation rate. So it's common to have velocity sensors in the ductwork, which speed up the fan as the filter loads. I hope that makes sense, but you'll come across this time and again when you do that sort of project. Okay, to move on to, well, I'll show you a HEPA filter. Again, from the same source. Email air handling. Does that come up?
Yeah, we can see it.
Good, thank you. Okay, HEPA filters for critical air environments. So there's various types and sizes. I'm not going to go through all this, but again, there's technical data there. And I've made a note there, usually about 400 pascals for a loaded filter. I should mention that in an air handling unit or system that serves a critical environment, let's say an operating theatre, an air handling unit will have pre-filters, which will be at G4, F5. It'll have deep bed filters, which will be F8 or F9. And then it'll have HEPA filters at the terminal where the air comes into the theatre, which are H14. So if the pre-filters, the panel filters and the deep bed filters are maintained the way they should be, then it's going to take a long time for the HEPA filter to load up to 400 pascals. So even though that's your design basis, you know, it's going to take a long time to get to that level, but that's what you should allow for anyway. And just going back to the NCC, which I've highlighted there. So that the part that's got a cloud around it here refers to HEPA filters. So it must not exceed the higher of 200 pascals when clean, or the filter design pressure drop when clean at an air velocity of 1.5 meters per second. So that's what you need to comply with. As I said, 1.5 might be quite high. For an operating theatre, it's more like 0.6. So the pressure drop will be much lower than that. Grease filters used in kitchen exhaust hoods to prevent grease from entering the exhaust ductwork. They're made from stainless steel to prevent corrosion and allow regular washing. So they usually do just a changeover, like I was saying before. Someone comes in with a set of changeover filters, takes the dirty ones away, puts the clean ones in, and takes them away for cleaning. Designed for quick removal and replacement. That's the standard type of filter for a standard hood, not for a specialised hood. They're normally selected at face velocities of 2.2 to 2.3, but they're not rated on velocity. They're more rated on airflow requirements, which is the same thing anyway. Now, note that the NCC requirements don't apply to kitchen exhaust systems. Okay, so you're not constricted by the pressure drop requirements, etc. And I'll show you that highlighted E4 there. Requirements of A, B, C, and D do not apply to kitchen exhaust systems. So you don't have to worry about those pressure drop requirements. I've got some, again, from the same source. There's some ratings on kitchen exhaust filters. So, and there's some charts there for pressure drops. Some proprietary kitchen exhaust hoods are supplied with integral filters and cleaning systems. Example from Stoddart's or Air and Odour Management Australia. And their websites are there. If you're doing a large commercial kitchen, it's quite likely that the kitchen designer will want a specialised exhaust hood. So it would be typically from Stoddart's or Air and Odour Management, or there are others. These systems usually have lower airflows, which is an advantage in your ventilation systems. I haven't got an example to show you, but you will find that if you design in accordance with AS 1668 Part 2, if you design a kitchen exhaust hood for a large cooking area, you'll have a very high airflow. And so the ductwork is bigger, the fans are bigger, and so on. But with these specialised exhaust hoods, the airflow can be a lot less. I won't say what percentage less, but it might be even between 50 and 75% of the other method. So they have an advantage for us in that way, and they usually come with their own filters and cleaning systems. Okay, carbon activated filters are used in ventilation or air conditioning systems to eliminate objectionable odours or chemicals in gaseous form. This is not common, but applications include outside air intakes for kitchens, clubs, shopping centres, and hospitals. Excuse me. I'll give you an example of an application that I've had. That was a hospital. We had outside air intakes serving wards. They also had a helipad on the top of the hospital, and so the helicopter was landing above the wards, and obviously we're having outside air coming in through the air handling units to feed the wards. So there was a risk that the fumes from the helicopter would be drawn in to the air handling systems. There were some controls to do changeover, but we still had to bring outside air in, so we used carbon filters in the outside air intakes to absorb or adsorb the fumes from the helicopter. So that's one application, but There are quite a few, but they're not common. Filter sizes are generally 600 square, with a thickness of options of 200 or 600. Normally selected at face velocities of 2.5 meters a second for the 600 deep option. Manufacturer's data will provide information on the rated airflows for the different sizes. So this is where it gets a little bit tricky because you don't know what filters are going to be used, but you've got to base your design on something. So information is available. Again, I can show you. Again, from the same source, there's technical data available for the different filter sizes: 600 by 600 by 200, 600 by 600 by 600, nominal sizes, rated airflow capacities, and the clean resistance. So information's out there if you come across this. The clean pressure drop can be quite high. 100 pascals, for instance, is typical. So you need to include that in the static pressure calcs. And the NCC applies to these filters as well at an air velocity of 2.5 meters a second. So put there, that reference that I've been looking at is aesenvironmental.com.au. It's only one manufacturer. There's quite a few out there. So just be careful when you're selecting filters that you get the right data. Any questions on filters before we move on? No? Okay. Another thing we come across, excuse me, quite often are weatherproof louvers. The reason I'm mentioning these things is because there's always tricks with these things that you need to be aware of. So I'm just trying to help you understand that it's not just pick a size and she'll be right. It's not that simple. Weatherproof louvers are used in ventilation and air conditioning systems for various reasons, including outside air intakes, natural ventilation. So you've got a warehouse, a factory, you might use louvers to ventilate the factory. Plant room ventilation, exhaust air discharges. I'm sure you've all come across filters. What I'm going to try and do is give you a little bit more insight so that you don't get into trouble with sizing of filters, because it can be tricky. They're available in single stage and two stage. Single stage louvers have one set of horizontal blades for the air to pass through, whereas two stage louvers have a second set of blades, which are normally vertical. Single stage louvers are the most commonly used, but two stage may be used where extreme weather conditions can cause water to enter the building. So if you've got louvers on a windy side of a building, a wet and windy area, you might have a two-stage louver to prevent the water coming in. We're going to focus on single-stage louvers in this talk because they're the most commonly used. The air pressure drop across louvers can be significant and increases with the number of stages. It also depends on the size of the filter. No, size of the louver, sorry. Intake louvers. NCC Part J 54D specifies maximum pressure drops allowable across intake louvers. For a single stage louver, the allowable maximum pressure drop is 30 pascals or 60 pascals for two stage. So I'll just show you that again. So highlighted in green there, pressure drops across intakes louvers must not exceed the higher of. Single stage, two stage acoustic louvers, I'm not going to talk about those, but that's where you're absorbing noise, either coming in or coming out of an area. And other non-weatherproof louvers, 30 pascals. So you need to be aware of that, again, when you're doing your static calculations and when selecting louvers. Selecting louvers is all very well if you can find good information, and there is good information available, but that doesn't mean that's going to be the louver used on your project. So you need to be able to specify the parameters of selection of the louver. Single stage louvers, we say generally have a free area ratio of around 50%. But that's dependent on the size of the louver. So if you're using a small louver, they can be much lower than that. I'll show you some data shortly. For a 50% free area, this means that the face velocity or the air velocity at the face of the louver doubles as the air flows through. So it might be, if you take the outside area of the louver, so it's 1 metre by 1 metre, and your face velocity is 1.5 metres a second, then the passage velocity as the air passes through the louver will be 3 metres a second. So it'll double for 50% free area. That makes sense? It's generally accepted that, I like this one, generally accepted that air travelling at 3 metres a second is on the threshold of carrying entrained water in the event of rain. So if it's raining outside and you're dragging air in at a passage velocity greater than 3 metres a second, you're probably going to bring water in as well. This is the critical part with intake louvers. You don't want that to happen. You don't want to be bringing water into the building or into your ductwork. So we aim to limit the louver passage velocity to a maximum of 3 metres a second. Absolute maximum. So this is a few things here you want to be careful of. In other words, single stage louvers should be sized for a maximum face velocity of 1.5 metres per second, assuming a free area of 50%. If the free area is greater than 50%, it may be possible to increase the louver face velocity. Okay, so reduce louver size, but make sure that the data is correct and the correct louver is installed. And I've worked on projects where the problem is the louvers are usually specified by an architect and procured by a builder, and then the mechanical contractor is stuck with it. And that can be a major problem. Okay, this happens a lot. So the architect's done a design. He said, I'm putting this louver here. That's your outside air intake. Guess what? It's not big enough. So then you have to try and negotiate to get a bigger louver, or engineer your way around it. And better if you can have a bigger louver, I can assure you. Yes, so I've just said, make sure that the data is correct and the correct louver is installed. The data can be difficult to obtain, so play it safe. I think at this point, I will show you some data quickly on louvers. And this is not a bad document to refer to. It is hard to find data on louvers. Years ago, there was a company called Air Grills who manufactured outside air louvers. And their data was really good, but they don't exist anymore, so you can't go there. That's not to say that the actual louver will be by Air Grills anyway. But this information here is some quality air equipment. You can look them up. They're an Australian company. These grills, I think, are made in Sydney. I have used them, and they're quite good. So has that come up? Can you see that?
Yeah, we can see it.
Yeah, good. Thank you. They make them in all shapes and sizes. So if you want a round one, you can get a round one. But generally, they're rectangular or square. So there's a few options. There's 48mm spacing. And what that means is, just bear with me a second. So there's a cross-section of the louver here showing the louver blades, which are obviously on an angle to stop the weather coming in. So the air comes in and goes up through the louver, and the spacing between those blades can vary. So the first lot of data is for 48mm spacing between blades. That's quite tight. And you can see on this table here, for the different sizes, nominal neck size, which is the size at the back of the louver that you connect a duct to, 200 by 200 through to 600 by 600. The free area is given in square metres there, so you can calculate the free area ratio. Free area factor. This is a handy table. Nominal neck height. For the nominal neck height, which is the vertical height of the louver, for a 48mm spacing, there's the free area factors, 0.55 to 0.65. 58mm spacing, 0.52 to 0.65. And for 100mm spacing, 0.51 to 0.7. So as long as you have a nominal neck height of 300, you could achieve the 50% free area that I've been raving on about. And I'm raving on because it's important to be careful with these louvers. I did work on a job in Sydney that had been designed and was designed, the building was designed by the architect, obviously. I got involved in the project pretty late, after everything was installed. I arrived in Sydney and I was asked to go and check out things, why things weren't working and so on. We're having trouble with the outside air intakes, and it was because of the louvers. The contractor had put in louvers that were, the builder put in the louvers that were specified by the architect. The contractor connected to them without checking out the size and the airflow rates, and we had lots of problems getting the outside airflow rates because of the pressure drop through the louvers. They wouldn't have complied with the NCC, but it was too late to do anything about it. We just had to go with it, and we had to upgrade all the fans to achieve the airflows. So be careful with those. It turns out that a face velocity of 1.5 metres a second tends to cause a pressure drop around 30 pascals. So compliance with the NCC is achieved in that case. But don't take my word for it. You need to check that. But these things kind of just come together. If you follow the basic rules of thumb, they do work. And you end up with the result that you need. And the NCC is written by people who've worked in the industry and understand how these things occur. And they try to be practical in most cases. Pressure drop across the louver is proportional to the square of the air velocity, which is the same for everything. Therefore, increasing the louver size will reduce the face velocity, which reduces the pressure drop, but the cost of the louver will increase. And you've got to have somewhere to put the louver on the building. So you'll find that this is an issue that comes up again and again when dealing with architects or builders. Be insistent about the louver sizes that you need. So I've just said that there. Stick to the fundamentals. Otherwise, there'll be issues with pressure drops affecting the fan performance, noise, and water ingress. So noise is another issue. If you've got a high face velocity, it'll cause noise. So be careful on the discharge louvers as well, because sometimes designers tend to think, well, it's only a discharge louver, so we're not going to have water coming in. We can go to a higher velocity. But a higher velocity means a higher pressure drop exponentially and more noise. The NCC doesn't specify specifically the pressure drop allowable across the discharge louver, but it does state a maximum of 30 pascals for exhaust grills. So it's the same, basically the same thing. This 11.11, exhaust grills must not exceed a pressure drop of 30 pascals. So that applies to exhaust louvers as well, in my opinion, and for energy efficiency to keep the pressure drop down. So I've said in terms of energy efficiency, it's important to minimise pressure losses where possible. It's recommended that the face velocity for discharge louvers doesn't exceed 2 metres a second. Now, this is just a rule of thumb, which will result in a passage velocity of around 4, again, depending on the free area. So if it's if you've got a larger free area, your passage velocity will be lower and the noise will go down, the pressure drop will go down. But NCC governs what you can and can't do. in terms of pressure drop. So that was a quick coverage of louvers. Any questions on that? There's some rules of thumb in there that that tend to work. I've worked in the industry for many decades, and it's worked for me over the years. And I've had robust discussions with architects on many occasions about the size of the louvers, and I've worked on projects where the louvers have been specified. Like I did a big hospital in Brisbane that had hundreds of louvers, and they were all supplied by the architect, and we spent weeks and weeks going through them all, trying to get data on the performance of them. The louvers came from China. Getting data was very, very difficult. Anyway, we sorted it out in the end, but it's important to be aware of that. So now I'll have a talk about flexible ductwork. You've all come across this. It's widely used in ventilation and air conditioning for supply air connection between the rigid duct and the diffusers, and return air between the grills and the duct, exhaust duct between the grills and the duct. Back to the NCC again. Flexible duct used in air conditioning systems is required to be insulated, but not normally insulated for exhaust systems. You can get acoustic rated flexible duct, and sometimes you might use that in exhaust systems to try and absorb some noise. It has some effect, but it's not great. Insulation requirements are specified in NCC Part J 5.5. Excuse me a sec. And for flexible duct in an air conditioning system, the insulation must have an R value greater than or equal to 1. So I'll show you the part from the NCC. Can you see that? Right, J5.5, ductwork insulation. We're going to talk about ductwork insulation and pipework insulation in more detail in session 12. But just to show you the highlighted part here, ductwork and fittings in air conditioning system must be provided with insulation having an insulation R value greater than or equal to flexible ductwork 1. Okay, now to me that's a good thing, because it's a good development, because previously the previous editions of the NCC said that the insulation of flexible duct had to be equivalent to the ductwork insulation. And so if you've got an insulation thickness of, say, 50 millimeters or more, the duct is not flexible anymore. You can hold up a 3 meter length of flexible duct and it stands up. So that was not practical, because flexible duct is meant to be flexible. So they've settled on R1, which is generally about 40 millimeters thick insulation. The Aerotechnical Handbook again provides a chart for sizing flexible duct. Some people wonder where they can go to find this out. Well, there is a chart there. The chart is based on straight duct, so additional allowances are required for changes of direction. Most companies develop their own standards for sizing flexible duct at different airflows. But as a guide, I would aim for a friction rate of less than 1.5 pascals per metre, or up to 3.5 metres a second, whichever is lower. I'll show you that chart from the technical handbook. So if you're stuck for sizing flexible duct, you can look this one up. There's some notes at the bottom. It's a guide only. Again, many people manufacture flexible duct and they might have different ratings for their airflow and pressure drop. But this is a guide if you need something to refer to. It obviously has the advantage of being able to manoeuvre around obstacles, which is the reason we use it, to make that final connection. But it's important to keep the duct as straight as possible to avoid high pressure losses. avoid sudden changes of direction, and ensure that a straight section of duct is used at connection to grills and so on. So when you connect to a grill, you often see that they twist the duct around and just bang it straight on top of the grill. That can cause issues unless it's supported properly and you've got a nice long radius. If you're using chill beams, which is not so common now, but the manufacturers of chill beams will stipulate the maximum length of flexible duct you can have, and I think it's about 1 metre. It's got to be straight. It's straight connection. Otherwise, they won't work properly. It's quite common that poorly installed flexible duct can lead to unsatisfactory performance of an air conditioning or ventilation system. Common problem is when flexible duct is squashed or severely restricted in the ceiling space. This happens a lot. Consequently, the required airflow will not be delivered, and the problem may be very difficult to rectify once the ceiling construction is completed. So when you're on site, beware of this, have a look at it, have a look at how the flexible duct is going to be installed or has been installed. And if you see severe restrictions, get the guys on site to straighten it out. I've seen some terrible situations. Usually after the fact, you get your head in the ceiling and have a look, and you can see that it's been squashed in between trusses or something, and that's why the air's not coming out. So that's one of the first things in troubleshooting. If you're not getting enough air, check the flexible duct, because it might be squashed. There's an Australian standard, AS 4254, on ductwork, part 1 and 2. Part 1 is for flexible duct, and it details requirements for duct construction and installation. So these standards are worth looking at and getting to know what's in there. It's referenced in the NCC, and therefore compliance with it is mandatory. The duct installers on site probably haven't even heard of AS 4254 Part 1, so it's sort of up to us when we go to site to make sure that they install it correctly. NCC Part J 5.4C has some additional requirements for flexible duct in terms of friction rate in the index run and a maximum length of 6 metres. The length of 6 metres has been another development that's come from the industry, where there used to be a stipulation in the NCC that flexible duct could not exceed 3 metres, but that was making it extremely difficult on site to do everything that needed to be done. So they've changed it to 6 metres, which is good. And most flexible duct, well, you can buy 3 metre lengths, but more commonly it's made in 6 metre lengths. That makes it easier. If you've only got short runs, there's no point using a 6 metre length if you've got a short run of flex. You get the shortest you can, which is probably 3 metres. And as I said, when you're inspecting on-site installations, check that it's been installed correctly and ensure that defects or potential problems are rectified before ceilings are installed. So that's important. So just a few things I wanted to talk to you about this morning. They're probably considered minor elements of our air conditioning and ventilation systems, but they are important and they need to be dealt with in the correct way. So I just wanted to highlight some of those things to you. That's the end of the notes. What else can I show you? Oh, I've got, well, this is the NCC that I just mentioned. So the pressure drop in the index run across all straight sections of rigid ductwork and all sections of flexible ductwork must not exceed 1 Pascal per metre when averaged over the entire length of straight, rigid duct and flexible duct. Bit of a mouthful. The pressure drop of flexible duct sections may be calculated as if the flexible ductwork is laid straight. So when you're doing your static pressure calculations in your index run, the average pressure loss must not exceed 1 Pascal per metre. So that's important to know that. But you do have some concession on the flexible duct, and it must not account for more than 6 metres in length. it says in any duct run, well, that's any branch to a diffuser is the way to interpret that. Any questions? Okay, well, I hope that's helpful to you. A lot of this stuff is drawn on my experience over the years of things, hurdles that we've had to jump over again and again. And that's why I'm trying to give you guys some awareness of basic design fundamentals when you're doing these things. So hopefully that's useful. Next week, we're going to continue with some more elements of air systems along the same lines, just to give you an awareness of things to look out for when you're putting these systems in. They might seem pretty basic, but they're all important. Okay. Thanks for your attendance, and we'll see you next week.